Hey, I'm Rob Brock, and welcome to the third and final embedded containers video. You've watched our introduction video, and you sat through the webinar. Hopefully you've learned something from both, or they may even have tugged at your curiosity about containers. Maybe, just maybe, you even checked our white paper on the subject, found here. Right, in this final video, Toradex go over their OTA, or over-the-air devices, and how they are used and compare when in use by different industries.
Hello everyone, welcome to this session entitled Automotive Grade OTA for Industrial IoT. That's OTA as in over-the-air updates. This presentation is brought to you by Toradex. My name is Brandon Shibley. I'm CTO of Toradex. Toradex is an embedded computing company with the mission to make embedded computing easy. We do that by offering reliable system-on modules featuring NXP i.MX processors. We're an NXP Gold partner and we have offices around the globe to provide regional sales and technical support. This is a look at our product portfolio, which consists of three families of system-on modules. They all feature NXP i.MX SoCs, and our newest family, Verdin, there at the bottom, is available with NXP i.MX 8M Mini and i.MX 8M Plus. We provide support for Yocto Project Linux, Windows Embedded Compact, as well as our industrial IoT Linux platform called Torizon, which includes support for containers and over-the-air software updates, and I'll be sharing more about that during this session. Our solutions are commonly embedded into products in industrial automation, healthcare, transportation, test and measurement, and smart city, including building automation, just to name a few. I mention that because today we'll be discussing over-the-air updates for industrial IoT, and these are the typical application areas that we work closely with our customers on. So let's talk about how industrial IoT compares to automotive. And well, first of all, why automotive? Automotive is at the forefront of dealing with large-scale over-the-air updates. And we can start by first talking about safety and security, both critically important for automotive. I don't even need to explain why. Vehicles are dangerous and expensive. And safety and security are also important for many industrial IoT applications. In automotive, updates must be managed for a mostly uncontrolled, highly distributed fleet of vehicles. They may be on or off, with or without connectivity. There is no guarantee when a vehicle will be available to receive an update or if it will be connected long enough to download a complete update. It must be resilient. The same is often true for industrial IoT systems. The supplier model for automotive is notably complex. An OEM commonly integrates solutions from various suppliers or vendors. The system must accommodate software updates being provided from different suppliers who in most cases do not work together or trust each other. As I mentioned, there is an element of trust, or lack thereof. The OEM has ultimate authority over the software in the vehicle and often delegates authority at various levels to other suppliers or integrators. Finally, in modern automobiles, there are dozens, even hundreds of processors in a vehicle that may need updated. The need for updates to the software or firmware of multiple processors or controllers is also commonly present in industrial IoT. So let's have a look at the diagram here. Notice this Acme IoT company at the center of the diagram. Imagine they build a product using a SOM and software from Toradex as part of their product, and sell that to various customers. Perhaps it's a medical device and it's being sold to different hospitals. Each customer or hospital in this example has a fleet of these devices. Now imagine the product has some premium AI or machine learning features that some customers can enable from another supplier who can train and deploy a machine learning model based on the needs of a customer. Just like in automotive, the device may have secondary processors. So you can see how a solution that is proven in automotive to deal with complexities of fleet management, of software updates, could be well suited to address the needs and complexities of industrial IoT. So allow me to introduce you to Torizon. It is the industrial IoT software platform that Toradex provides. It is based on open source technology, so much of what I'll discuss here isn't proprietary to Toradex, although we do integrate it with a lot of other great technology, providing extensive support for our NXP i.MX-based products, providing long-term support and continuously integrate, thoroughly test, and regularly release the latest and greatest software. Consider Torizon to be a case study for the technology. Today I'll be highlighting the open source technology we use for over-the-air updates. I'll describe why we chose to work with the stack we have and highlight the similarities of industrial IoT to automotive as it relates to continuously shipping software to embedded products. Key objectives for Torizon were to allow many of our customers to achieve fast time to market using our ready-to-integrate platform. We have customers in many different industries specializing in many applications, so we value an open stack that gives our customers choice and fosters an open ecosystem for collaboration. Connectivity and security are vitally important to the platform, as are the principles of Devops, a means to regularly and rapidly integrate, qualify, and deploy up-to-date software. So we need to provide tooling and integration that minimizes the time, effort, and risk that go into transforming source code to software that's executing on an edge device. We expose an extensive software ecosystem with Torizon, and of course we provide a secure and reliable over-the-air update solution. It is built upon an automotive secure update framework, and for the remainder of the talk I'll be talking about the software used in the update stack. These are some of the primary components of our OTA solution. They are also used by automotive-grade Linux. OSTree, it's like Git, but for file systems. Think about what it means to apply a Git workflow to the file system. You can commit changes to the file system. You can pull changes from another OSTree repo. You can check out a specific revision of the file system or revert back to a specific revision. And that's quite powerful. It allows for some really cool workflows. It's file-based. It uses hard links. Most of the file system is mounted read-only. This helps ensure immutability, which I'll explain a bit later. There are writable parts of the file system for logging and things, but we want to carefully revision control the system's root file system, not allow all the devices in a fleet to drift apart with different system configuration and different component versions. It's both bandwidth efficient for downloading updates, only downloading individual files that need to be updated, and it's storage efficient on the device flash. It supports deduplication and only stores a single copy of any unique file. It supports atomic updates with the use of hard links, and the integrity can be verified. Aktualizr is a device-side update client. It is Uptane compliant, which I'll describe shortly. It secures the updates end-to-end and takes care of update verification and ensures confidentiality. And finally, Uptane is an open and secure automotive software update framework, which this OTA system implements. It is described as the de facto standard for automotive updates. Let's talk about Uptane, and to do that, we must point out that Uptane is derived from another update framework called TUF. TUF. It literally stands for the update framework. TUF has 4 key design principles. Separation of trust. That's the distribution of responsibility for the signing of metadata. Therefore, if a signing key is compromised, it will not affect other users. Threshold signatures. Requiring a certain number of signatures to authenticate a file before the update can be downloaded. Explicit and an implicit revocation of keys. That's a way of replacing compromised keys so that they are invalidated and can no longer be used maliciously. And keeping the most vulnerable keys offline. Certain signing keys can be kept offline making them harder to steal or compromise. And those are the 4 key design principles of tough. But in automotive, there are some additional issues. The system can be made up of many different processors that all need to be updated. Not all of those processors are especially powerful, particularly when it comes to cryptographic computing, and not all the parts of the system trust each other. The components are developed by different vendors, and there's need for compartmentalization. So the resulting solution contains 2 different repositories, both utilizing tough. One to store the images themselves. The image metadata is signed offline. And then the second repository, called the director repository, is used to tell connected processors which image they should install. Its metadata is signed online to balance security with speed and efficiency. This allows for a separation of responsibilities, one for the software itself and a separate responsibility for controlling fleet updates. Additionally, allows for delegating signing authority on various levels. For example, to authorize other suppliers of software or to grant control over software updates to a fleet or subfleet. And finally, Uptane added support for both full and partial verification. Since some secondary processors lack the cryptographic horsepower to do full verification, a partial verification method is possible. So let's talk about some of the common update vulnerabilities that this update framework addresses. The most obvious and concerning is using the update system itself to install malicious software. This is why we use code signing to keep inauthentic software from being used. But what happens if the keys are compromised? Then an attacker will have the ability to install seemingly authentic but malicious software. So going back up to those design principles, most of these principles deal with preventing, mitigating, and or recovering from key compromise. There are read vulnerabilities or sniffing updates. An attacker can read the contents of the software update to steal intellectual property. So to avoid this, the update should be encrypted. There's denying updates, right? This prevents the system from being able to download or install updates. Obviously an issue if the system has known vulnerabilities. And finally, there's denying functionality or causing the system to install the wrong updates, either outdated software with known vulnerabilities, right? This is software that's been signed, but it's outdated, or incompatible software versions that make the system function incorrectly. Attackers can make the system endlessly update, causing the system to exhaust resources or go into reboot loops, things like that. So Uptane is one of the most secure update frameworks available, guarding against a very broad threat model. In addition to employing a secure OTA update system, I want to highlight the importance of Devops and software lifecycle management. Secure connected devices must be kept up to date, and we prefer to do that using continuous integration, testing, and deployment to ensure that software is kept up to date, tested, and ready to ship, not waiting for the next big vulnerability to find out that there are integration or quality issues with the latest software. Some related topics here are configuration management and revision control, ensuring that change is managed and that there is a clear history of change and that we carefully control what revision of software is deployed into production. Quality assurance, making sure that our quality standards are met for any software that is deployed. Automation and reproducibility, together with traceability, we want to ensure clear traceability between specification, design, source code, binaries, test results, and deployment, and the whole chain of integration and delivery should be reproducible. Finally, we embrace immutability. I like to use the analogy of treating a fleet of devices like cattle. Not like pets, handling each device individually does not scale well, and it can be painful when a fleet-wide change is needed. Instead, we want to manage the whole fleet from a fleet level to ensure consistency. Operating on the same revision of software ensures uniformity and predictability. Earlier I mentioned immutability when describing OSTree. Our OTA technology, together with OSTree, helps us achieve these goals. These are some references, and I encourage you to check out these projects: Uptane, Aktualizr, and OSTree. And I also encourage you to visit Toradex at toradex.com and learn about Torizon. If you've got a Toradex system on module, you can try Torizon OTA for yourself at Toradex Labs. That's at labs.toradex.com. And would love for you to try to yank the power on your board just as it's performing an update. Verify the resiliency of the update system. Poke at the automotive grade security. And I'd love to hear your feedback. So with that, what I want to leave you with is a short little demo video of Torizon OTA. Thanks, everyone.
This has been great. We should do this again sometime. But for now, goodbye.